July 25th, 2024. My name is Neese and today I'm smiling. And I'm smiling because today is the day we finally give you ORCA 6. Now ORCA 6, that just sounds like an update to a program. Something that has been there for a long time and that got tweaked here and there. And what I'm trying to explain to you, what I bring across to you today, is that ORCA 6 is so much more than that. Because ORCA 6 essentially is a brand new quantum chemistry program that was built up from the bottom, that was built from scratch. But I think what sets it apart is that it was built from scratch after 30 years of experience of doing that. And that is what we believe gives this program a future, a very bright future. It is also a very emotional moment for me, I have to say, because I've been living with this for so long, and over the period of the last 3 or 4 years, it felt like reliving a big part of my scientific life and fast forward, and deleting so many lines of code that are related to intimate memories and how the world looked like at the time it was written. But there's only one way forward, and that way forward, that leads to the future, and that future starts today with ORCA 6. And of course I'm coming to you just as the spokesperson of a large team of people who made this happen. Actually, 2 teams of people who made this happen, together with our collaborators all around the world. And before I say anything else, I want to show you the people that made this happen. Now, and these are the teams at the MPI in Mülheim, at the MPI für Kohlenforschung, and the team at Facts in Cologne, the company that is a spin-off that sells ORCA to industry and that is incredibly successful in the market. And together we have joined forces to bring you what today is ORCA 6. And of course at the MPI in Mülheim there is a privileged set of people, a group. And that group is the ORCA development team. And I want to give a shout out to that team. So that team consists of Frank Venmos, Axel Kozlowski, Dagmar Lenk, Ute Becker, Kanten Sivalingam, and Dimitrios Liakos. And they are the people who are involved in basically everything that you're going to see today. Those are the people who make it happen, to make sure that we have compilers and libraries, that everything builds, that they're debugging, they're cleaning up after people, they're testing and testing and testing, and then they test again. All right. And with that, I want to briefly recall where ORCA is coming from. We have done that so often in ORCA users meeting and other places. But now the ORCA user community has grown to a loud and proud number of 70,000 academic users, and that is not counting the many, many people in industry who use ORCA commercially. And so I just want to spend a few minutes explaining to you where ORCA 6 is coming from and why the evolution was the way it was. Now, ORCA started when I did my PhD as a biochemist at the University of Constance, and I was tasked with the job of explaining an EPR signal, electron paramagnetic resonance, that 2 enzymes, 2 metalloenzymes had in common that contained copper, cytochrome C oxidase and nitrous oxide reductase. And these 2 enzymes, they share a peculiar EPR signal. And I was asked, what's the structural origin of that? And I understood that I cannot possibly answer that question without having a way of predicting the spectra from a structural candidate. And the only way to do that was quantum mechanics. And so that is when I started learning quantum mechanics. And at the time, of course, we had ridiculous computers and et cetera, et cetera. But I wrote the first version of the ORCA program in the beautiful language of Turbo Pascal, and we used it. And I think these MCD and absorption spectra and EPR spectra you see there, these are the reasons why ORCA exists. And at the time, of course, the only thing that was possible was semi-empirical quantum chemistry, and we used the INDOS Hamiltonian. And by and large, it was extremely successful, and it could compute those spectra of these open shell transition metal ions very, very successfully. Now I'm doing fast forward to July 1st, 2021, almost exactly 3 years ago. That is when we released ORCA 5. And ORCA 5 was the first step in a complete revolution in the ORCA program. When Corona hit, we were all grounded, and that was the moment where I decided that it was time to come back to an old project that I had, and that led to the Shark Integral package. And the Shark Integral package then turned out to be very successful development, and that made a major transition from ORCA 4 to ORCA 5. And we were so proud to release it to the general public in a big online event just like the one we're having now on July 1st, 2021. It was very enjoyable, and since then the number of ORCA users has skyrocketed. We're almost doubling every year, and that leads to the number of about 70,000 now. So the major advances in ORCA 5 were the Shark Integral package that drastically improved performance, new COSX implementations that drastically improved performance, new exchange correlation and COSX integration grids that were machine learned and that significantly improved speed and accuracy and robustness of all of these calculations, and many, many other features. Now, let 25, 30, 50 people work on code for decades, and eventually what once was beautiful and shiny turns into a mess. And that is exactly what happened to us. And I'm not pointing fingers towards anyone, and the person I would have to point fingers most strongly at is myself. But that is exactly the situation we were in 2020 before we started rewriting the ORCA code. And it turned out that new incoming students had bigger and bigger problems contributing to the code because they would find it so hard to read. And what happens then is that the process of messing it up by copying and pasting and just to play safe, do this or that, is accelerating. And so eventually the only thing that helps is to rewrite the code. But nobody's given these resources. And in that respect, I think we have done something unique. Never before, to the best of my knowledge, has a major quantum chemistry program been rewritten from scratch. And now we have. And that is our ticket to the future. And that is a ticket to the future where we can program, where we can develop much more efficiently in a much more streamlined way with a much better infrastructure in a way that is sustainable and healthy. And so now we have to say, rest in peace, ORCA. It lived from 1995 to 2022, roughly, the old ORCA code. So that makes it a member of the Club 27. And so out of the ruins of the old ORCA code, there emerged ORCA 6 as a new program, a clean program, where we have rethought and streamlined everything from scratch. And what I want to do next is to walk you through the architecture of ORCA 6 so that you understand why so many of these modules that you're used to as ORCA users are gone for good, and how the new program works and functions internally. And so that is then the architecture of ORCA 6. I have to say that is largely, not exclusively, of course, not nearly exclusively, but that is largely my contribution to ORCA 6. I've worked on this like I probably have never worked on anything else in the last 4 years, and every minute that I had for programming in the last 4 years went into doing this. And it's a tedious project. There is no doubt about that. And that's why it's good if somebody does it who doesn't need to find the next job, who needs to write papers, who needs to write grant proposals, etc. And so you will see the wonderful, wonderful, beautiful, gorgeous work of all of the other people that were contributing new code, new ideas, new methods, etc., etc. And the tedious work on the infrastructure, that was largely mine. And so in ORCA 5, we put Shark into all, not all, but many of the strategic places. And so the code basically looked like, if use shark, then do this, and then else. There were thousands of lines of legacy code. Now in the new code, there is just simply a single line, a call to a driver, and that means that millions of lines of legacy code were actually deleted. And new and highly streamlined code was written. And all compute-intensive tasks are now handled by a handful of highly optimized functions that are triggered by the drivers and not even by the ORCA main code itself. And all of the approximations that we have, like Rij cos x or Rijk or Rij onx or whatever comes in the future, are handled by these drivers. And so the person programming an algorithm in ORCA doesn't need to take care of any of that. And that is what makes it so powerful and makes it so easy to use for the developers, the actual developers and the future developers. And so in doing so, I have really thought deeply about how do we want to organize the information flow, ideally, in a quantum chemistry program to avoid redundancies and to make everything as simple and direct, as transparent and as streamlined as possible. And so what ORCA 6 is based on is a shell structure. And that shell structure has as its core the shark package. And so that is generating the integrals and that is doing all the integral transformations, etc. So the compute-intensive tasks are like largely delegated to the machine, and the machine is the shark machine. And then ORCA is the layer above it that is interacting with the user, that is organizing the whole flow of the calculation, that is producing the output for the user. And the ORCA core code now interacts with Shark through a very small set of routines that are the Shark drivers. And so inside ORCA, we don't make a big fuss out of differentiating all of these approximations that we have, or whether it's Hartree-Fock or DFT or whatever else it is, but that is all taken care of by the drivers. Now inside the ORCA code, we only we would implement a solver and say, hey, we need a Fock matrix, and then we call the Fock matrix driver, and then the driver decides everything on whether it's DFT and what flavor of DFT and what grids are needed and what auxiliary basis sets are required, etc., etc. And now above ORCA itself is the next layer of software, and the next layer of software, these are software layers that organize whole workflows, like series of jobs. And so you will later see the compound facility inside ORCA, or FACTS, is producing a program that's called Wiesel that is very successful in organizing workflows. And over that would eventually be a graphical user interface that the user can interact with. And so if there is such a shell structure and it's being respected, then of course each shell has a very well-defined meaning and a very well-defined list of tasks it has to perform, but it should not nose into the other program parts territory. And if you divide it in this way, then of course everything can be programmed very cleanly. And I would say we are 95% there. There still is a little bit to be done. You as a user of ORCA, you will not see that. We will complete it after this one, but it's 95% what it should be. Now let's look a little bit at what's gone and what's new. So in ORCA 5, we had the ORCA A&O program that is gone because generally contracted integrals are now calculated by Shark. Then there was the ORCA GTO program that was calculating the one-electron integrals and was organizing some of the workflow. And eventually we decided that's a very inappropriate name. And now there is a program that's called ORCA Startup that is doing these exact terms. So they set up the grid, they calculate the one-electron integrals, the pre-screening matrices, etc. Like many of these tasks of this kind. Then there was the ORCA SCF program, and the SCF program usually is pretty much the first program that is being written in a quantum chemistry program, and so it's also the one that's being experimented the most with, and that means it's also the one that's messiest. And our SCF program, after 30 years, started to be really, really messy. So one day I decided enough is enough, deleted it, and wrote a completely new program. And that program is ORCA Lean SCF. And I will talk about this in a moment. And it's accompanied by a second program that's called ORCA Gas. And ORCA Gas is producing the initial gas for the SCF calculation or the CAS SCF calculation. And it's logically disconnected from the actual SCF program, and that helped cleaning up the code quite a bit. And now then there was the CP-SCF module in ORCA 5 that was solving the coupled perturbed SCF equations. And there was a problem with that, calling it from different routines, and there were problems with it, like the same perturbations were handled again and again and were repeatedly solved for, and that was inefficient. So that's all gone now, and it's all part now of a new program that is called SCF response, and that is solving the SCF response equations, and it's accompanied by other response modules that I will talk about in a minute. Then there was the SCF Hess program that was calculating the Hessian at the SCF level, and that is gone too, and it is part now of the more efficient infrastructure that we have, and that is now calculated by a new program that is calculating all properties inside ORCA, and that is called ORCA Prop. And that is independent of whether these the calculations, the CAS SCF calculation or a DFT calculation or a Hartree-Fock calculation or a coupled cluster calculation. ORCA Prop is a program that is calculating the properties. Similarly, ORCA EPR NMR was a program that was calculating EPR and NMR properties. That is gone now, and it's also inside ORCA Prop. And there was a particularly nasty program, the ORCA SOC program, that was calculating the spin-orbit coupling integrals, and that is also gone now, and it is inside the same functionalities inside a new program that is ORCA PropInt, and ORCA PropInt is a central program for calculating all property integrals. And now let me show you how that works together. And I will make the point of response properties, so those properties that can be written as a derivative of the total energy. And let's say there's a property M that can be written as the first derivative of the total energy with respect to a perturbation M, and that then requires just the one particle electron or spin density matrix and the property integrals over the integral kernel operator M. And there are many such properties. The dipole moment would be one of those, or the isotropic hyperfine coupling, or the dipolar hyperfine coupling, or the electric field gradient. They're properties of that type. And then there's a large number of properties, so-called response properties, that can be written as a second derivative of the energy, and they require basically two ingredients. They require property integrals, they require the density or electron or spin density matrices, and they require the first derivative of the electron or spin density matrix. But at that point, it does not matter where they come from, whether that's a full CI calculation or a CCSD parenthesis T calculation or a CAS SCF calculation or a DFT calculation. The only thing that is really required is the one particle electron and spin density matrix and its response to an external perturbation. And that means there is so much commonality in these properties that it's really wasteful to keep repeating that code in every single module, like in the MP2 and then in the MDCI module and then in the CAS SCF module and in the DFT calculations, etc. And so we decided to build a centralized structure that is taking care of these response properties all together. And that works the following. So the user interacts with the main program. The main program then either calls first the guess and then the SCF or CAS SCF program. And then after the SCF or CAS SCF program, there will be the post-SCF calculations. That would be MP2 or coupled cluster or multi-reference perturbation theory or multi-reference coupled cluster, etc. And these produce a one particle density matrix and a one particle spin density matrix where appropriate. And now these densities are stored in a density container. So that's a centralized quantity that stores all densities inside ORCA 6. And of course, it comes with all the metadata, like by the module that it has produced, whether it's electron density or spin density, or what type of density it is, whether it's a derivative, whether it's for an excited state, etc. All of this is stored in the density container. Now, the next thing that happens is that the main program is calling the prop-in program. And so the main program looks ahead and understands each and every property integral that is needed along the way. And so once that is known, there's a single call to the prop-in program that is then producing these property integrals and storing it in a central place again, and that central place is the prop-in container. So now the next thing that we need is then the density derivatives, and so that is then what's happening next, is that that the main program is calling the various response programs. And so that can be the SCF response program, so that the SCF RESP that I've just talked about, but it can also be any of the other responses that ORCA 6 knows that previous versions of ORCA didn't know. For example, there's the CAS-SCF response program now that I will talk about a little later. Then there is the MP2 response, and there is also a coupled cluster response. And that coupled cluster response is residing in the AutoCI infrastructure, and I will talk about that later too. So then we have everything, the response densities are generated, and they're also stored in the density container. And so now the task that is left now is for the main program to call the property program, and that's ORCA prop, and that is taking the densities, the response densities, and the property integrals from the respective containers, and is calculating all of these first and second order properties. And the nice thing is, the property program doesn't really know how the flow of the program was before. It simply finds an eligible density and will calculate the property for it. For example, in the same run, if you do, say, a Hartree-Fock calculation, an MP2 calculation, and a coupled cluster calculation, the property program will first find the SCF density, then the MP2 density, maybe the relaxed and the unrelaxed one, and then the coupled cluster density. And it will calculate the dipole moment for all of them, like next to each other, and print it. So you can really easily and nicely compare those properties calculated at various levels of theory. And so that also means that if there is a new method implemented into ORCA that is producing a density or a response density, no further code needs to be written in order to immediately have all properties available that can be computed with that density. And so that is very nice because it separates logically the calculation of the wave function and the calculation of the molecular property. And so that is a really essential part of the way the ORCA infrastructure was restructured. Now let me talk a little bit about the new modules. And the first one is the ORCA Lean SCF program, and it's certainly the most important one. So that is completely newly designed self-consistent field program. It has two different DIS solvers. It has a much improved version of the SOSCF solver, and it also has a second order converging TRA solver, and that is something that ORCA 5 also had. It's extremely clean code that is easy to follow and to extend. So let me give you an example. While like deleting the old program, I was following the old workflow of the old SCF program. I found out that the total energy was calculated up to 4 times during a single SCF cycle, just to be on the safe side, because people didn't really know exactly whether the total energy that was stored in the object was still the right one or not the right one. And then of course you do what you do, and like you recalculate it just to be on the safe side. So sometimes like the energy was recalculated 4 times, and sometimes it was even calculated like with an extrapolated density from the DIS procedure, meaning that those energies weren't variational anymore. None of that nonsense is happening anymore. Lean SCF does everything in an extremely transparent, linear, and streamlined way. Now, the old program had like bits and pieces where parts of the Fock matrix were calculated here and parts of the Fock matrix calculated there, and then maybe there was another approximation that was coming through the back door, and then everything was different again for ROHF. No longer true. There is a single call to a sharp driver that's calculating the fog matrix, and that's it, nothing else. But the most important part, and that is why it's called Lean SCF, is that the old SCF program used too much memory. And the reason for that was that we kept multiple copies of these matrices in memory all of the time for each core the calculation was running. There were fog matrix, density matrix, overlap matrix, s to the minus 1/2 matrix, MO coefficients, H-core matrix, etc. You name it. And that severely limit the size of system that could be treated on decent parallel machines with the old SCF program. And now Lean SCF is based on the idea that you only have in memory what you absolutely need at this given time. For example, when you calculate the fog matrix, the only thing you need in memory is the fog matrix and the density matrix, but not the MO coefficients. When you diagonalize the fog matrix, you need the fog matrix and the MO coefficients, but not the density. So what Lean SCF does is to only keep in memory what's absolutely required for the given step that it computes, and everything else resides on disk. And that is done extremely carefully. And you will later see that this is a game changer. It allows SCF calculations that are much larger than anything that was possible before. Right? We also, in the process, ironed out some kinks in the existing solvers, and we got rid of some unnecessary and legacy features and options that were there for no good reason anymore. And so Lean SCF is really very much at the heart of the new infrastructure. And so it leads to far lower memory consumption, more robust convergence, and it's more reliable to use as a black box. And it usually also needs fewer iterations in the old program. Now, as I said, the density container and the property file are two things that are left over after a run of ORCA 6, and they're there for you. We made them for you. And so you can use them, you can enjoy them, you can look at these densities, you can plot these densities, you can read these properties, you can manipulate these properties, you can integrate them in your workflow in whatever way you want, and there will be much more information later in this talk, and then also in the other talks by Dimitrios Liakos and Dimitrios Marganes and Nicolas Foglia. All right, so now we are back. And now I'm happy to present you benchmark data. So we now dig into the core functionality of the program. Now, and of course, it's a vast amount of methodology that can be tested. And let me start you by one experiment that we did that was enjoyable a little while ago. And so I was going back to an old slide that I once presented in Walter Thiel's group meeting in the early 2000s, and at that point we were starting to use the guinea pig we always use, which is the vancomycin molecule, and at that time it was giant, 176 atoms, and it had like a couple of thousand basis functions, and I was super proud to present to Walter that I could do like an SCF calculation on that molecule in a mere 6 hours. And was happy at the time. And today, took that calculation, ran it on my laptop, and it took 1 minute and 34 seconds. So that's a factor of 280 roughly. And we were asking ourselves, where is that performance gain coming from? Is it hardware or is it algorithm? And so what we did something that is not trivial. So we took out 25-year-old ORCA code from various stages of ORCA development, and we compiled and linked them using modern libraries and ran them on modern machines with the current version of ORCA, all run under identical conditions on the same computer. And that means the difference in timing here just simply reflect algorithmic improvements. Now, of course, we know how much the hardware speed increased over the course of the last 20 or so years. And that is a mere factor of 7 or so, right? I know that it's a difficult comparison because modern CPUs are very tricky, but let's say it's around a factor of 7 coming from the hardware. But here are our algorithmic improvement speeds. So ORCA at 2005 let's say that is normalized to like a calculation time of 1. And so what you see here, that there was an enormous increase in efficiency going from ORCA 4 to 5, and that is largely the shark infrastructure and the new COSX infrastructure. But now look what's happening here. Now ORCA 6 is smoking ORCA 5, right? And so for a small double zeta basis sets, we're now 18 times faster than ORCA was in 2005, and we're like a whopping 165 times faster than for a larger basis set than ORCA 5 than ORCA was in 2005, and that is just the algorithmic improvement. And so you see that the algorithmic improvement is dwarfing the hardware improvement, and there still is a lot of room on the top. There still is a lot of room on the top, but I show you now all the improvements that we've made in going from ORCA 5 to ORCA 6. Let's start with the calculation here. That was a fun little calculation I did on my laptop, same molecule, vancomycin. And so I started with like the CCPV-DZ basis set. These are 2,400 basis functions, and that went in like by and large 20 minutes with a peak memory of far less than a gigabyte. Okay, that's not a big deal. With the triple zeta basis sets, it's 4,700 basis functions, and then it only takes a half hour. It's a half hour on a laptop, single CPU, right? Then quadruple zeta is 8,500 basis functions. That took an hour and a half. Pentuple zeta, that is 14,000 basis functions. That took about 6 hours. And even the sextuple zeta basis functions, basis set with more than 21,000 basis functions, that still runs on a single core on a laptop in less than a day. And so you will see that you can go much faster, and that has like tons of super high angular momentum functions up to H and I, etc. And that is a direct consequence of the lean SCF. So that is what the lean SCF makes possible. It allows you for much larger calculations on modest hardware than any of the previous program versions. Now, a big part of the speed up that we have then for hybrid functionals are due to improvements that happened in the chain of spheres exchange approximation that, as you will know as a proficient ORCA user, is a default in conjunction with hybrid density functionals. And that is the love child then of Bernardo de Souza from FACTS, and he has basically adopted the COSX code and has tweaked it and tweaked it and tweaked it, and after he tweaked it again. And it was really worth it. So you see that like COSX in ORCA 6 is far more efficient by a factor of at least 3 to 5 or so than it was in ORCA 5. At the same time, Bernardo has been able to improve its accuracy. So you have here calculations on glycine chains up to 100 glycines, and like the error introduced by the COSX approximation is consistently below 0.02 kilocalories per mole. So you can basically really use the COSX energies interchangeably with the exact ones, but the speed ups that you're having from the COSX are enormous, right? They're over a factor of 100. And so that is a big part of the success. And now what is possible now with ORCA 6 is to run these enormous SDF calculation. So that is a calculation, a DFT calculation with more than 10,000 atoms and more than 70,000 basis functions. That is the insulin with more than 2,000 water molecules solvating it. So this is a calculation that is possible with ORCA 6 as we give it to you today. And that is not the end of the road. We could go bigger than this, we just didn't. And so we don't really know where the boundary is, but I'm quite positive that with ORCA 6 you can go beyond 100,000 basis functions for a DFT calculation. So that means huge is routine now. So this is apomyoglobin, 2,500 atoms, and about 20,000 basis functions. And so with PBE and the double zeta base set, that takes like just 2 hours and 50 minutes. And with R2 Scan 3C, it takes 9 hours and it's 31,000 basis functions, or with WB97X D4, it doubles the database at less than 5 hours. So you see that like these are calculations that were enormous, outstanding, difficult just a little while ago, and they're absolute routine now. And that is because the infrastructure, every single aspect of the infrastructure was tweaked to perfection. Oh, near perfection. There, let's see what we come up with in 6.1. But you see, there is so much that has happened under the hood, and so much that needed to happen under the hood to make this reality, and we're proud of it. Yeah. Now, here's an example for embedding, and so you see also in embedding calculations with ionic crystals, there are enormous speedups of more than a factor of 4 that ORCA 6 gains over ORCA 5. And so now this is a theme that will continue and continue. Now, one thing that the new infrastructure made possible that I'm super happy about, that since there now are not 500 places where integrals are calculated, but basically one, we could put in symmetry, finally, and exploit symmetry. And that has been the work of Axel Kozlowski, and so he implemented the petite list algorithm with full point group symmetry. For example, here for C70, with D5H symmetry, the order of the group is 20, and the speed up he's getting is 19.3, so it's nearly perfect. So right now, symmetry can be used, not unfortunately still absolutely everywhere in ORCA, but we will eventually get there. So the petite list and symmetrization for finite point groups is available for single points. There's a symmetrization of the gradient, so it will really keep the point group that you started in, and there is a symmetrization of the Hessian. There also is a symmetrization and symmetry blocks in TDDFT, CAS-SCF, and MRCI. So these are all programs that use symmetry, not all of them to perfection, but eventually they will. So the petite list algorithm for CP-SCF calculations in the Hessian calculations, that is something that is in the works, but will only be given to you in a later release. And also the full use of symmetry in coupled cluster calculations, that is something that will have to wait for a future release. But we're very happy with what we have. Now, ORCA 6 also has a more robust geometry optimizer, and that again is tweaking. Then it's like caring about the details, and the person who has really done that is Bernardo de Souza. And so you see here in these optimizations, so these were about 75 test systems that Bernardo ran, and the red line is the number of cycles in the geometry optimization taken by ORCA 5, and the black lines is the number of cycles taken by ORCA 6. And so you see that it's almost, with very few exceptions, ORCA 6 takes fewer geometry cycles than ORCA 5, and in those very few cases it takes more, it usually finds a deeper minimum, or a minimum in the first place where ORCA 5 converged to a saddle point. And so that is something that we understand, deeply understand, for computational chemistry is of utmost importance, that you reliably and efficiently converge a geometry to a minimum. And here and there have been reports that ORCA 5 led to saddle points with very small imaginary frequencies, and that's not a shame, but it's a nuisance. And so in ORCA 6, basically all of these small negative frequencies are gone thanks to the very careful tweaking that that Bernardo has done on the geometry optimizer infrastructure. There also have been quite a few improvements in transition states and NEB calculations. So you can, it's not uniformly obviously, but this got tweaked to the point where it can be up to 10 times faster than it was in ORCA 5. So in this small example, that was GFN 2XTB on 60 processors, and so you see that that ORCA 6 gets there in 8 seconds and ORCA 5 gets there in 85 seconds, so that's a factor of more than 10. And we realize that is really the heart and soul of computational chemistry, is to calculate energies at fixed geometry, calculate geometries, calculate Hessians, and calculate transition states. And we believe to the bottom of our heart that what we're giving you now is world-class and state-of-the-art, at least state-of-the-art, if not state-of-the-art defining. And we're very happy about that, we're proud about that. Now, SCF Hessians, that is, of course, we all know Hessians are really, really expensive. Now, our test case here is the everolimus molecule with about 151 atoms, and with DEF2-TZVP it has 2600 basis functions. And so when you look at the timings of the individual steps, there are 3 major steps: right-hand side calculations, the CP-SCF calculations, and then the explicit terms in the Hessian. The most expensive one is usually the CP-SCF, and it's also the one that scales the worst. And so now let's look. So these are all ORCA 6 calculations as a function of the number of processors. And so what you see here, that up to about 8 processors, these calculations scale wonderfully. They really scale amazingly well, but then the scaling starts to deteriorate and the timings don't get that much lower. Now these absolute numbers are great, so I'm coming to that in a moment. Then that's right, these are still super efficient calculations, but the scaling with the number of processors wasn't quite optimal. Now let's compare ORCA 6 to 4 and 5. Now same molecule, same system, same basis set, same everything. And so you see that ORCA 6 is by itself much faster than ORCA 4 and is a little faster, maybe 10-15% or so, than ORCA 5. And that is due to the infrastructure and the integrals being tweaked and the cos-x is better and all of these things. Yeah. However, we had another idea. And that idea is something that Ute and I had, and let's say, okay, so it scales great up to about 8 processors. So why not like finding a different strategy where we define groups of 8 processors and then distribute the perturbations that we need to solve for, like in groups of 8 processors on the available processors. So for example, if you have 64 processors available, that would be now a notation that says PEL 8x8. Yeah? And so now you see that is a strategy that is like very successful. And that brings down the calculation times because now everything scales, right? Then so inside each group, the 8 processors scale well, but then since the groups are independent of each other, they basically parallelize perfectly, right? And so what's happening here is that the calculation times are up to a factor of 4 faster than without the group parallelization. And so now we're like factor of 4 to 10 faster than ORCA 5. Right? And so with the PBE functional, that whole Hessian calculation, right, on that big molecule with a decent basis set takes about half an hour, right? And the B3-lib calculation just takes 2 hours. And that is really, really a big difference, right? Because that is something you could wait for days in like previous versions of the program and probably also with other quantum chemistry programs. So that is something that we're very happy with and that we're excited about how much faster these Hessians can be calculated. Now, ground state properties. Now let's take the same molecule and calculate the proton NMR spectrum. These are 86 shielding tensors, 668 spin-spin coupling tensors, meaning we have to solve for 219 imaginary perturbations and 504 triplet perturbations. And so this is the time in minute, like with PBE functional, it's 2.5 minutes for the SCF. With PBE and with B3-lib, it's only about a factor of 2, right? And so these are still like 2,600 basis functions together with the PCJ1 NMR optimized basis sets. And of course, here the rate limiting step, because we're solving for over 700 perturbations, is the CP-SCF. But still, it goes in 44 minutes for PBE and in only 202, which is less than 2.5 hours with B3-lib. And so that is pretty smashing. So when we compare ORCA 4, 5, and 6, so you see an enormous progress here, right? So the same calculation takes 18,000 seconds in ORCA 4, 7,500 seconds in ORCA 5, and only 2,100 seconds. So that's more than a factor of 3 faster in ORCA 6 than in ORCA 5. And it's even more dramatic for B3lib, where ORCA 6 is more than a factor of 4 faster than ORCA 5, and that is a direct consequence of pooling these perturbations and the whole new property infrastructure. So it's a factor of 5 to 10 relative to ORCA 4 and a factor of 2 to 4 or so relative to ORCA 5. So we're super happy about that. So you see the entire infrastructure really got, the overhaul was absolutely worth it, because the whole thing like really runs like a well-oiled machine. Now TDDFT calculation, I only have to show you something, I can show you something where these are all ORCA 6 calculations, 91 atoms, so it's about 2,000 basis functions with def2 TZVPP and about 4,000 with def2 QZVPP, and that is by no means the end of the line. You can go much, much, much larger with it. But look how fast these calculations are. We're like solving for 20 roots here, and so that is done in about 2 minutes for the SCF and like less than 4 minutes for the TDDFT with PBE and the def TZVPP basis set. And so it's a little less than 10 minutes, and for the old calculation, less than 15 minutes for the B3lib calculation. And even with the quadruple zeta basis set, so B3lib is done in about an hour and PBE is done in about 20 minutes. So you can, I mean, the TDDFT in ORCA 6 is also really, really efficient. Now, there also is the ICE program. So the ICE program is a variant of the CIPSI algorithm from Jean-Paul Marieux, and it's a selecting CI algorithm to treat large active spaces, and you can basically treat arbitrarily complicated spin coupling patterns. Here we have an example of a 4-iron 4-sulfur cluster, and that is code that Vijay and I have worked on, and it got tweaked and tweaked and tweaked, and it performs now. So the biggest calculation that was done here to test it was a calculation with 70 electrons in 44 orbitals. That's a very large active space, but this is something that can be done rather straightforwardly with the ICE program and the ORCA infrastructure. And so that is something that can be done as a matter of a couple of days. Still an expensive calculation, but absolutely doable. So now let me summarize performance in ORCA 6. So ORCA 6, as you've seen, the infrastructure has seen a major redesign, and all jobs run consistently through a small set of highly optimized routines, and that means there is consistent and robust performance throughout the entire program. All of these jobs can be run efficiently with segmented, partially generally contracted, and generally contracted basis sets. The progress in the integral generation, digestion, and code streamlining make most jobs run faster than before. Many of these jobs dramatically faster than before even. The progress in the solvers and optimizers, they lead to faster and more robust convergence for nearly all jobs. There is also progress in parallelization, and that makes most jobs scale better in parallel than before, and particularly Hessian's and response calculations with group parallelization. And now importantly, we have paid so much attention to memory consumption and memory optimization, and so that has been reduced dramatically, especially for the SCF and significantly for gradients and Hessians, and the program is respecting the boundaries of the memory you give it with the maxcore command more rigorously than before. And so the speed ups are partially dramatic for SCF, for geometry optimizations, for Hessians, for response properties, and for TDDFT. And so we think that this is a major asset in ORCA 6, and we can't wait for you to give us feedback on how well we are doing. So that concludes the second part of this talk. So we take All right, so now we're back here, and now we're back for the third and last part of my presentation, and that is to walk you through all of the new features of ORCA 6. So let's start with SCF and single reference. So one thing that was implemented in the SCF program, and again by Bernardo de Souza, is the Delta SCF procedure. And the Delta SCF procedure is a systematic way of converging the SCF to an excited state, not necessarily a physically accessible excited state, but one where you move electrons from orbitals that were occupied in the ground state calculation to an empty orbital and then reconverge, but making sure that you keep the excited electronic configuration. And so that is something that is extremely convenient. And before you needed to play tricks and had to pray a little bit that the program would cooperate, but now you can converge reliably to these excited states. And there are many, many places where you can use it, for example, for calculating electronic coupling matrix elements in electron transfer type problems, and there is a lot to be explored, and the ORCA manual will tell you more about it. Now, something that was requested time and again in the forum is to be able to use electric fields and also to optimize molecular geometries and calculate molecular properties in the presence of external electric fields. Now, it happened that like SCF calculations in the presence of MP2 and MDCI, they say like single point calculations in the presence of electric fields have been possible in ORCA forever. We just never documented it. But now, thanks to Zico and Wang, we have not only documented it, but Zico has also made it possible to run geometry optimizations and then transition states and spectra and everything in the presence of finite electric fields. So the only thing you have to add to the input is then the X, Y, and Z components of that external electric field, and the program will make it happen. Now, here's something really cool. So when you press a button, ROHF, in the head of a computational chemist, they mostly think about it as a variant of UHF, where you can converge to a high-spin system that has the singly occupied orbitals and doubly occupied orbitals instead of spin-up and spin-down orbitals. But as a matter of fact, ROHF is so much more powerful than that. And thanks to Diego Eliza da Costa Gouveia and Dimitrios Maganas, we have developed a procedure where you can converge the ROHF for an arbitrary spin coupling. So for example, here is a chain of antiferromagnetically coupled nickel centers, and so basically the spin coupling goes up, down, up, down, up, down, up, down, with two unpaired electrons on each side, and then if you have an even number of sides, you come up with a total spin of 0. And so you cannot do this with DFT, you cannot do this with UHF. You get a broken symmetry solution that is not physical. But you can actually calculate an S equals 0 exact spin eigenfunction now using the general CSF ROHF. And the only thing you have to do there is to tell the program that you have a user-defined CSF and then define the spin coupling among those singly occupied orbitals. And so you see, while you can get a somewhat better description for similar systems with CAS-SCF, CAS-SCF is infinitely more expensive, right? So the general CSF ROHF is basically a little more expensive than UHF, but not that much. It gets more expensive the more open shell you have, but by and large, it runs at a similar speed as UHF. It also converges well. And so now you can generate spin eigenfunctions for systems with many unpaired electrons and a spin coupling that is not necessarily high spin, but can be anything. So we're super happy about it, and we will explore it a lot in the future in the fields of magnetism, antiferromagnetic coupled solids, antiferromagnetically coupled transition metal oligonuclear clusters, etc., etc. So that is something exciting. Now, here's something that also was really, really requested and that is important, and now it was done. in a way that is much more efficient than it was done before. And that is the open shell similarity transformed equation of motion coupled cluster. And so Marcos Casanova-Pace, he has implemented the IP EOM CCSD, the EA EOM CCSD, the SD EOM CCSD, all for open shells. So now it's completely on the same footing as the closed shell code that was used a lot by our users out there. And so finally now that can be done on equal footing now for the UHF. And Marcos has also implemented covalent separation for XAS calculations with the SDUM CCSD methodology. And here is a small set of transition metal calculations where he shows that the SDUM delivers results that are in stunning agreement actually with reference CC3 calculations. So we're super happy about that, and we're more than happy to give you these new features here. Now, Yang Guo has been our friend and collaborator for a long time, and he has done stunning work in DLPNO NEFPD2, DLPNO NEFPD2 F12, and all of this was part of previous ORCA releases, but now he has also combined all of that with the cluster in molecules methodology, and so that is allowing for much larger calculations because this parallelizes better because of the fragment division and separation. And it combines beautifully, really beautifully with the DLPNO methodology, where it allows for enormous calculations with 2.5, 3,000 atoms and more. And what he has also contributed to that code is, to this release is then the combination of the cluster in molecule, DLPNO, CCSDT, with explicit correlation F12. So we hope that many of you will check that out and will make good use of it. Now there also is, that's a minor detail, a full-featured stability analysis. There was a stability analysis in the old code, but it didn't allow for all efficient approximations that we had in the rest of the code. It couldn't do CPCM or Cosmo and these things. Now the stability code can do that, and it also can, at least upon request, automatically look for lower energy solutions. So for example, here I'm starting a calculation using the stability analysis as a UHF closed shell for the O2 molecule, and you all know that's not what the lowest singlet state should be like. And so in the presence even of, like, say, CPCM with water solvent, it will take several iterations until it finds a stable wave function, and that stable wave function, of course, is a broken symmetry solution that is basically substituting for an open shell singlet. This is exactly what it should be. It's a 50-50 mixture of a singlet and a triplet, has spin expectation value of 1, and so all of this is automatic now. And there is no need to tweak anything, so you simply give that stability keyword in, and it runs just as it should. Then Stefan Grimme and his group, they have done a lot in updating our DFT capabilities, so there's quite a bit of new functionality in the scan family of functionals like hybrids, double hybrids, range separated hybrids, etc., etc. There is updates on the DFT-D methodology and functionals that are specifically parameterized, excuse me, together with the D4 correction. They've also put in a few more basis sets and then regularized MP2, and that is something that was also requested by our users quite a bit. So this is what happened in SCF and single reference calculations, but there are also new features in the multi-reference modules, and I think maybe the most important one, that is work by Spencer Leger and Benjamin Helmich-Paris, and that is the CAS-SCF linear response program. And that is a beautiful thing that you can do many, many things with. You can calculate a number of response properties with it. And here are the available properties that they have so far. It's electric field, quadrupolar field perturbations, magnetic field without GIAOs, and velocity perturbations. Now, this is just a start. Obviously, this is the start of something bigger, but we're super happy that this methodology exists, and I can tell you that this is complicated stuff, and it's really wonderful how Spencer and Benjamin worked through this, and we look very forward to see what next comes out. Then Benjamin has worked a lot on the CAS-SCF program and has made many improvements, many more than I could tell you here. But one specifically useful thing he did is to implement the Avas guess. And the Avas guess is something that really helps you to find the right active spaces that you desire by giving it a list of atomic orbitals that then the program goes through in a somewhat elaborate projection procedure to construct an initial active space that then is followed throughout the program. So, for example, typical target AO spaces would be the metal d or f orbitals or double shell active space and all of this. And Benjamin has put in very convenient keywords to do that. So that's super useful in practice, and especially so it frees you from like having to run separate fragment calculations or running a previous MP2 natural orbital calculation to select active spaces, etc., etc. So many of these calculations now can converge out of the box with a single keyword that specifies the desired active space. Benjamin has also implemented something that's quite hard to implement, but he has done it, and that is a full-featured second-order TRA converger for CAS-SCF. And so, specifically when the first-order converger that we have runs into problems, the TRA converger usually can get there and can get to very high accuracy. So it can convert the CAS-SCF to very high precision, and that is sometimes very necessary. So we are very grateful for Benjamin that he managed to do that, and that TRA is now available as a full general feature with the CAS-SCF program. Now here is something that interesting piece of history. So any general CI program that is making use of configuration state functions is faced with the subject of calculating these so-called one-particle coupling coefficients, and these are the matrix elements of the orbital replacements operators EPQ over configuration state functions I and j. And so basically we had a fairly nice way of doing that and storing that in a prototype coupling coefficient container. But the way we were generating our prototype matrix elements was let's say not quite optimal. And so Michael Rümmelt, who is in Berlin, and his students, they revisited that problem, and they found a recursive algorithm to calculate these coupling coefficients. And I have to say, I'm a bit embarrassed, but I'm also happy at the same time, because they compared their results with an older ORCA version. And so they found that for a 16-16 active space, and singlet coupling, so that is a nasty, complicated case, but nevertheless, the ORCA took 14 hours and their code took 13 seconds. So that's about 4 orders of magnitude. And Michael was kind enough to implement that algorithm into ORCA. Now that is the default, the old code is no longer available, and so now you're generating these coupling coefficients with equally high efficiency now by default, also for large active spaces, and we're grateful to Michael for doing that. Now, new features in relativity, and I'm very glad to say that Gorgi Stolchev has managed to implement the X2C scalar relativistic Hamiltonian, and so X2C is currently probably the most featured and most promising relativistic method on the market. And so we're using it like we use everything in relativity in a one component form, where we separate out the spin orbit coupling. But of course we have the X2C picture change correction on the spin orbit Hamiltonian and also on all property integrals. But one really nice feature that we have here now is that Gorgi implemented the analytic gradient for X2C, and so now there finally is a proper analytic gradient for an all-electron scalar relativistic Hamiltonian, and that is now definitely the method of choice for running all electron calculations on heavy elements. And at the same time, it's available also in all forms of property calculations, also for G-tensors and NMR shieldings and couplings and dipoles and polarizability, etc. So all of this is available now with X2C. At the same time, I and Gorgi too, we have collaborated on revisiting and streamlining the Douglas Cole-Hess infrastructure that we have. So now that's also quite nice and quite streamlined, and we plan to keep it. The Zora Hamiltonian is also still available, but we recommend to all of our users to pass on to the X2C because it has the most favorable feature set of all of these relativistic approximations, and that is what we will focus on moving forward. Now, I come to a subject that's close to my heart and where a lot of effort went into creating ORCA 6. Bits and pieces of it have been available before, but it made a huge leap forward in going from ORCA 5 to ORCA 6, and that is automatic code generation. And I personally believe this is the future of wave function theory and the only chance that we have to keep developing wave function theory in a competitive manner. So that is work of quite a number of people that have worked on it over the years. And I think like I should give credit to Marvin Lechner, then, as he really wrote the core of the present code generator, worked very hard on it, and when he graduated, then Stan Papadopoulos took over, and like these two people I think are the ones that brought the code generator infrastructure the furthest. And so Marvin has generated multi-reference, internally contracted multi-reference coupled cluster code, and as you will see in a second, Stan has focused on producing coupled cluster analytic derivatives. And then there's Ingolf, and Ingolf worked on it for a year, but amazingly efficiently, and he has implemented all things Müller-Placid perturbation theory up to fifth order. Hang Su is doing an admirable job in doing coupled cluster response properties with the code generator. Then Emily Kempfer has joined the team, and she already contributed wonderfully to it, especially spin adapted triple excitations. Emily figured out how to do that properly, and rest of the work is coming soon. Then with the next release, there are some really cool features in the making. Also, Monisha Ravi is working on some really cool stuff with the code generator, and Ria Kayal is focusing on higher order coupled clusters. So the sky really is the limit when it comes to code generation, and one is mostly bound by creativity. And this is exactly how it should be. And of course, the whole ORCA development team has contributed to that. So there is a quite substantial list of methods that are implemented using the AutoCI infrastructure, including the whole Müller-Placid series up to fifth order. And I think we would have loved to also give you sixth order, but that didn't quite happen. And then there is coupled cluster, singles and doubles, energies, densities, and gradients. And that is something that the ORCA program never before had, and we're super happy about that. And then there's also CCSD parentheses T, and there are also energies and densities that we never had, and gradients that we never had, and that was probably one of the most requested features for coupled cluster in ORCA, and now we have it, and we're having it thanks to the efforts of that wonderful AGE team. And then there's also higher order coupled cluster. So with this release, we are happy to give you CCSD full T, so that is available with the code generator. And then there's also the internally contracted multi-reference method, so FIC MRCI, FIC SIPA, and even MRC CCSD, which are very, very computationally heavy methods for which we only have energy so far. But you can expect that now that there's so much work on the infrastructure of the code generator and it's producing really good code, that there will be a lot more development and methodology following in the next years. And so here you see that like the machine generated and the handwritten code are almost identical in efficiency. And like I would say ORCA has a really quite good CCSD code, especially for closed shells, and the generated code is just as good. And I think that's quite an achievement. And like when we started out, it wasn't quite like that then. So there was a factor of 2, 3, 4, 5 or so that the generated code was slower, but now it's same speed as like the best handwritten code that we could come up with, and that's really awesome. And now analytic geometry gradients with AutoCI, they're reality, they're tested, they work with frozen core or without frozen core for RHF and for UHF, for CCSD and for CCSD parentheses T, and it was an enormous big effort by Stan, and we're really happy that he pushed through that and that we can give that to you, and we're now really curious to hear how you will do with our new couple cluster gradients. And then Hang, he's working on really very cool stuff, but for this release he already gave you then couple cluster polarizability, so there is linear response with AutoCI, and there is a lot more to come in the near future when we release the next ORCA version. So Hang is on a fantastic way to produce great stuff. And Ingolf, with the Möller-Placid work, then I think that is really quite interesting because it's non-iterative, and for many well-behaved systems, MP4 is very similar accuracy to coupled cluster, but it can be had almost a factor of 10 faster under circumstances, and it is a really nice work that he did there. He also contributed a lot to optimization of the AGE infrastructure, and we're very grateful for that, and so we're happy to give you that in that release too. So here are the estimated upper limits of what's possible with the code generator right now. So for energies at the singles and doubles level, so that would be CCSD or MP4 SDQ, we think we can go up to about 1200 basis functions, which is pretty large. And for the gradient, up to about 750 basis functions. That is pushing it, but it's possible, and there's a lot that you can do with that. It still will require patience, mind you, because these are high scaling and to the 6 methods, but it's possible to do that, and the generated code is no toy code. This is code that you can really use in practice. And for parentheses T or full MP4, including triples, obviously, because of the increased scaling, it has to be lower. So we think that we can go to about 450 basis functions or so for energies, and for gradients, probably on the order of 320. But mind you, there still is a lot that you can do with that many basis functions. For full T, we don't know yet, but of course it's even less for the parentheses T. And for UHF MP5, which is the most expensive method that we have right now, so it's around 100 basis functions or so. I don't think that will occupy a big space in practice. But so you see that like there is substantial things that you can use for actual real-life calculations. So now in summary, the code generation enables the implementation of impossibly complicated methods like multi-reference coupled cluster or higher order coupled cluster, and it reduces development time from years to, well, not hours or days, but weeks or months. Then it can produce hardware-specific code, it can ensure consistent quality and high reliability, and I believe that code generation will play a centrally important role in the future of wave function-based quantum chemistry. And it can be made almost as efficient or better than the best hand-optimized code. So I think there's a lot that still is possible with code generation, and I think the first fruits you can now enjoy, hopefully, with ORCA 6. Now, more stuff. Now, environment effects, solvation and embedding. There's also new things there. And thanks to Miguel Garcia-Rata, she has worked a lot on this and has done a really beautiful job in doing CPCM and all kinds of other solvation methods. So there's an improved isodensity surface scheme for surfaces that make these calculations more accurate. These grids are also larger than before, and so that needed to be compensated for by improving the integrals, and so that's something that Bernardo and I did. So the electrostatic potential integrals are much more efficient than they used to be. and allow for really, really efficient CPCM calculations on large molecules with high accuracy that have none of the artifacts that sometimes go with these methods. And also Miguel has implemented the PTES scheme fully for DLPNO CCSDT, and that's important because now you can run the DLPNO couple cluster in solution just in the same way as you would do for DFT, and that's awesome. He has done the SMD analytic Hessian, he has done the dynamic radii adjustment, he has provided an interface to OpenCosmo AS, and he has implemented CPCMX scheme for fast salvation for semi-empiric. So all of this is like basically very much in the spirit of rounding off the standard functionality to be all around state-of-the-art leading technology in the business, and I think we have it. Now here is something stunning. Again, Bernardo is a magician, and he has implemented the GOAT procedure, and the GOAT procedure is a global optimizer. So it helps you finding the global minimum in complicated potential energy surfaces by jumping out of these local minima and eventually homing in on a local on the actual global minimum. And he has done many tests, and I know that also people in industry or people in academia have used it. They absolutely love it, and so please check it out. It's now officially available in ORCA, and it's documented in the manual, and we hope that that gets a lot of got a lot of airplay. The other thing that Bernardo did is to implement something that's a Docker. So if you have two molecular fragments and they interact, and you want to know how they're interacting, where are they interacting, what are the interaction sites, and if those fragments are complicated, it's really not obvious, and the Docker is taking care of this, and the Docker is giving you the ability to automatically find optimal interactions and docking geometries. Again, stunning methodology. And finally here is something that will also be really nice in practice, and that is the solvator. And the solvator is then a tool that Bernardo has designed to automatically explicitly solvate a molecule. And so that can be done as an alternative to molecular dynamics, and it helps then in situations where specific solvent-solute interactions are of critical importance. The solvator will come in. Again, everything now officially available in ORCA for the first time, much requested by the users, and we believe will be a big hit with our users. I'm glancing over it. I'm sure that Bernardo in his talk will do much more of that, and you can look forward to this. Now, here's also something we wanted to do for a long time, and now it happened, and the heroes here are Pauline Collinet and Benjamin Helmich-Paris, and they have implemented now finally the fast multipole methods for embedding calculations. And so that is something that, of course, when you have hundreds of thousands of point charges, eventually their interaction with the quantum system and even their interaction between themselves becomes very expensive to compute. And so here is where the hierarchical boxing algorithm of the fast multipole method does wonders, and that is a complicated theory, complicated equations, complicated integrals, and they have worked through it and have implemented it. And here's an initial application for a quite elaborate system that is a model for photosystem 2 that has 150 atoms in the quantum region, but 500,000 atoms in the classical region that are represented by point charges. And so you can see that the FMM is reducing the computation of the interaction time between the quantum system and the classical systems from about 4.5 hours to 3 minutes. So that is a huge progress in the embedding methodology that ORCA has available. And again, we're proud of it and we're happy about it, and we hope that many of you. Now, molecular properties and spectra. Now again, Nicolas has done some very high level, very precise work on implementing the exact field matter Hamiltonian for the calculation of transition moments, and he and Dimitris Manganas, he will tell you about that in detail. And again, it is now consistently available throughout the ORCA program, and we're super happy about it, and it helps in all kinds of calculations from MCD to X-ray absorption and everything's electronic spectroscopy. And they have also worked on the excited state dynamics modules. That's something that Bernardo has introduced into ORCA quite a while ago, when he was still with us in Mülheim, and now he continues doing that while he's at FACTS, and he has teamed up with Nicolas, and they have done all kinds of nice things. But I think one very specifically important thing is then the calculation of excited state lifetimes and fluorescence and phosphorescence rate. And they have done that. It's available now, and it works in practice. So as you can see from the graphics here, the correlation between theory and experiment is really very good, despite the fact that these are very complicated calculations. Nicolas has also worked on vibronic MCD, and so now for the first time ever, we are able to generate MCD spectra with vibronic fine structure and Hertz spectacular coupling using higher order transition moments or the full field matter Hamiltonian, and we're super happy about that. And really quite stunning calculations can be done with that. And there is a lot more that Nicolas has done that he will tell you about himself. Now, as I told you, Thiago did the general spin, or the general CSF ROHF, and of course then it's itching in your fingers to do something more with it from those ground states. And then the first thing that he did with it is then the general spin roses for the calculation of excited state spectra. So now you can take an arbitrarily complicated antiferromagnetically coupled systems and then use the roses to calculate spectra with it. And it sometimes really makes a substantial difference, like in the case of these coupled iron-manganese systems here, where you can see that the general spin roses is getting the job done, while broken symmetry DFT doesn't get the job done, and the high spin roses also doesn't get the job done. So that is a very exciting development. And Thiago is also able to show that it doesn't come at a premium. So it's a little more expensive than high spin roses, but not impossibly so. That's a development we're quite proud of, and I think that is very unique to ORCA. And it's an accomplishment that I don't think anyone had on the radar before, but now it's reality thanks to these efforts. Here's another thing that was quite requested by the users, and that is vibrational circular dichroism, and that is something that I have implemented together with Gorgi for FACTS, and so you see it works. It's basically a state-of-the-art implementation of a known theory, and it works perfectly. Now it's available for all of you in ORCA, and we hope you enjoy it. Alexander Auer has worked quite intensely on making the VPT2 module better, and since we overhauled the whole infrastructure, he also overhauled that, and so you can use that now to calculate vibrationally averaged molecular properties, and also a lot of enharmonic analysis. And again, it's all fully documented in the manual. It's available, and we hope that many of you who work in these fields, who are interested in these properties, can make use of it, right? So, for example, vibrationally average hyperfine couplings, G tensors, spin-spin coupling constants, and so on and so forth. So, and now that was a hardcore part of the quantum chemistry, and you see I'm almost out of breath already because there is so much that we had to go through. Now let's talk about workflow and interfacing, and that is something that is quite important to us. So now in ORCA 6 there are 4 levels in which we can interact with the outside world, and one is a property file that I already mentioned in the beginning, that is human readable, that is machine readable. It's a fixed format ASCII file that contains a concise summary of everything that was calculated in an ORCA run. And if you don't want to parse that, but you're a hardcore, die-hard JSON fan, we also give you a JSON interface, and I will come back to it in a moment, but the JSON interface basically allows you to translate the property file into JSON format, but it can allow you to do much more than that, and I will talk about that in a minute. But what I really want to talk about here is a compound job functionality. So compound jobs have been available already in ORCA 5, but thanks to the tireless efforts of Dimitrios Liakos, it's much more powerful now in ORCA 6. So please check out the manual and check out his talk later, because he will tell you a lot about all of these things that have improved with compound. So I only want to give you a few specific pointers. So ORCA pre-6 like very often used the new job command to like pull up a couple of jobs in one file. And that led to endless problems and discussions in the forum because these were interacting in a way that was undesired. Now with ORCA 6, Compound offers like a very clean way of getting the same result. So all you have to do is to start a compound block, and then for every job you want to do, you add a new step, put the job in, step end, and you start the next job, and then at the end you simply say end run, and then all the program will do is to go through these jobs cleanly and properly and without nasty interference, and then stop. Safe and clean. Now there's a lot of more complicated stuff, and I only glance over it. So the iterative optimization we have already discussed for ORCA 5, and so you can repeatedly run opt and frag calculations until there is no negative frequency anymore, and you found an actual minimum that is really nice, and that is implemented in a compound script. Something that was inside the ORCA code and now is delegated to compound script is the numerical calculation of the polarizability as a numerical derivative of the dipole with respect to an electric field. So that is something that's easily done in compound. Then of course you can do things like extrapolating an energy, correlation energy, and an SCF energy, for example in MP2 or couple cluster, and that's nice. But now you can do something even cooler. You can use inside a compound script these extrapolated energies and gradients to run a geometry optimization, and that is something that wasn't possible before. And now if you come up with a new scheme like to extrapolate a gradient or an energy, etc., now you can even do a geometry optimization with it. And that's really awesome, and Dimitris will explain to you how that works. And you can do also something that wasn't possible before, and that I've been wanting to be able to do for a very long time, and that is to use a compound scripting language to do BSSE optimization. So you have a compound script, and inside that compound script is all of the functionality to do then an optimization of a weakly interacting complex by taking account of the BSSE correction. Super cool feature. I believe that many of you will want to use it and will make great use of it in the study of intermolecular interactions. So you see there's near infinite opportunities in this compound scripting language, and we hope that you check it out and make good use of it. Now, ORCA 2JSON is designed to be your friend, and it is meant for you to interface to ORCA. So I already told you that you can use the ORCA to JSON interface to get a JSON format property file, but it doesn't end there. You can also use the ORCA to JSON interface to basically get all of the integrals that ORCA can calculate out into a JSON file that you can then use to run your own program. So you don't need to write your own integral generator. You can just use ORCA as your integral generator. And also something that we started experimenting with that I hope you give us feedback on, you can also use the ORCA to JSON interface to run it in reverse, to produce a GBW file that you can then use to feed ORCA, for example, if you want to feed your own orbitals from another program into ORCA, that is possible. And so going forward, we will not write specific interfaces to other programs. Whatever it is that you need should be in the ORCA to JSON interface, and we're committed to making this good and making it better and making it everything that you need in order to successfully interface ORCA. There are also nice enhancements in plotting and drawing. So there is an enhancement in ORCA plot. So ORCA plot can now understands all of the densities that are in the density container, and you can plot them, but you can do something really cool with it too that Dimitris Manganas has implemented. You can do algebra on them. For example, if you're interested, how does an electron density change when you go from Hartree-Fock to couple cluster? You can do that easily within ORCA plot using that lovely 1960s style menu that we have implemented there. But so you can basically get the couple cluster density from the density container. At the same time, you get the Hartree-Fock density from the density container. You can subtract them from each other, and then you can plot them, or you can do more algebra with it. Again, lots of exciting opportunities, and we like to see papers where you make use of that and like show really creative science that was enabled by this infrastructure. So, last but not least, obviously we put a lot of our heart and soul into creating ORCA for you. And there is one thing, and one thing only, that we ask our academic users in return for. Please cite our papers. And please do not put these citations in the SI because they're worthless for us there. Cite our papers, not only the one general ORCA paper, cite our method development papers. It gives us the airplay and visibility to continue doing this. And I hope that's not asking too much. We're not asking you to cite papers that are irrelevant or anything, but there is so much in ORCA that enables research that you are doing. Please show your gratitude by citing our papers. And in order to make that easier, we have created something that is the citation tool. So at the end of an ORCA run, we will now print a list of suggested citations ordered by the priority in which we think they should be cited or they contribute to their research. And if that is not enough, we also give you that same list in BibTeX format so you can import it seamlessly into any citation organization program. So my plea, please help us making ORCA, and you can help us in the absolute best way by citing our papers. Please do this. All right, and so there's no more excuse that like the manual is too big and I can't find it in the manual. The list of suggested citations is printed at the end of each ORCA run. All right, so we're almost at the end. So what's up next? And I was actually rushing into my office and then rushing in front of the camera so I can do it, but I took a quick picture of like the feature list that we already have made for ORCA 6.0. Oh man, that's not good. Sorry, it's too blurry, but I promise you, there is a substantial amount of great stuff coming. So now we have created the infrastructure to a point that is so powerful, so lean and so clean. The development is much faster and much easier. So we will give you so much more, and the list of features we already have planned in the pipeline for ORCA 6.1 is substantial, and we will not wait another 3 years. Promised. So we're planning to release ORCA 6.1 in the spring of 2025, and we promise there will be a lot of super, super cool stuff in it. So please stay tuned, look forward to it. And the last thing that remains now is to thank the many, many people who have contributed to this with all their energy, their patience, their enthusiasm, with all of their heart and their souls, their creativity and their ingenuity. And it's a great honor and a pleasure for me to work with these people. And we are so proud all together as the ORCA family to give you what we think is the by far best version of ORCA that we have ever produced, and we hope that you make good use of it. Thank you so much for staying with me. Thank you so much. I see all of you in the forum and now in the chat. Thanks.